Hello everyone, thanks for joining. I'm going to be talking about the paper Tyler's M-Estimator via Quantum Expansion, which is joint work between myself and Ankur Moitra. The topic of the paper is heavy-tailed covariance estimation, and our results are fast algorithms and nearly optimal sample complexity for shape estimation for elliptical distributions. Our results proceed by a new connection to operator scaling, which allows us to use geodesic convexity and quantum expansion to prove our bounds. To begin, let's discuss vanilla covariance estimation, in which we're given n samples from a centered Gaussian on Rp, and we want to estimate the covariance matrix sigma. There's a lot of applications for this problem, and the empirical covariance matrix is known to recover the covariance matrix in spectral norm when the number of samples is at least the dimension. However, this doesn't work in the heavy-tailed model, in which we still want to estimate the covariance matrix, but the samples we're given may have been adversarially scaled before we see them. This captures the problem of shape estimation for elliptical distributions, and it models the heavy tails found in finance and radar. Tyler's M-Estimator is a specific estimator for this problem, which Tyler defined in 1987 to be the solution to this equation. You can see that it's somewhat similar to the sample covariance, except for this denominator, which actually prevents it from having a closed form solution. Nonetheless, a lot is known about it. It exists with high probability if the number of samples is bigger than the dimension. It is asymptotically consistent, so when the p is fixed and the number of samples tends to infinity, then the estimator converges to the truth in probability. It doesn't depend on the adversarially chosen scalars at all, and there's an iterative procedure to compute it. Namely, our initial guess is the identity, and then we update each guess by plugging the old guess into the left-hand side of Tyler's equation and allowing the right-hand side to be our new guess. So a lot was open since Tyler's original paper, most importantly the number of samples. Is it behaving like the Gaussian case? Does samples need to just be on the order of the dimension? A partial answer by this, by Sell and Soloveichik, analyzed it in Frobenius norm and had some dependence on the condition number of the covariance matrix, but it's still not known for the spectral norm before our work. And we also look at this open problem of the convergence of the iterative procedure. It's known to converge, but it's not known how quickly. In fact, it's not even known if there's a polynomial time algorithm. The connection to the operator scaling that we point out in this work instantly implies that there's a polynomial time algorithm and that the iterative procedure converges in 1 over epsilon squared time. Informally, we achieve the same sample complexity as the Gaussian case up to a log squared factor. And regarding the iterative procedure, with similar sample complexity guarantees, we know that the sequence of iterates converges to the estimator in Frobenius norm exponentially quickly with exponential failure probability. More formally, we have to use this distance metric, which we use in part because it controls the total variation distance between the two Gaussians. But we basically achieve again in this metric sample complexity that is often what the Gaussian case needs by a log squared factor. And similarly, in this distance metric, the iterative procedure converges exponentially quickly. So what is operator scaling? First, let's talk about matrix scaling, because operator scaling is a generalization. Given a non-negative matrix A, are there non-negative diagonal matrices such that LAR is doubly stochastic? This is a classic problem, and it comes up in machine learning through regularized optimal transport. And there's a famous algorithm for it called Synchron's algorithm, which works by initially setting L and R to be the identity, and until one is satisfied, choose L to make LAR row stochastic, and choose R to make LAR column stochastic. Each of these steps is individually very easy to accomplish. And this procedure will converge if it is possible to find L and R, such that LAR is doubly stochastic. Now let's see how to generalize matrix scaling to operator scaling. So in matrix scaling, we have a non-negative matrix A, but in operator scaling, we're going to have a quantum operator, which is a tuple phi of matrices of each of the same dimension, but they needn't be non-negative. The analog of being doubly stochastic is these two conditions, and the scalings, rather than being diagonal, are just going to be invertible matrices. And finally, L and R are going to scale our tuple of matrices by simultaneously pre- and post-multiplying every matrix in the tuple. So why do we consider this generalization? Well, from this tuple of matrices, we can come up with a map from matrices to matrices, which acts to quantum states as non-negative matrices due to probability distributions. So it basically says what quantum states can undergo, what processes, stochastic and deterministic, they can undergo. There's a natural analog of Sinkhorn's algorithm for this, which is you alternately satisfy the first and second condition here. It's easy to choose L to satisfy the first condition, and it's easy to choose R to satisfy the second condition individually. So if you do it iteratively, it turns out to converge whenever there is a scaling. And this field has lots of applications. Comes up in the Braskamp-Lieb inequalities and analysis, communication complexity lower bounds, subspace detection, and non-commutative polynomial identity testing. So now let's see how to cast Tyler's M-Estimator as an operator scaling problem. If the samples are given by this tuple x, then we're going to construct an operator phi x by putting the vector xi in the ith column of the matrix AI. There's going to be n matrices AI. And other than this ith column xi, the rest is going to be filled in with zeros. Finally, what is the connection? Tyler's M-Estimator, sigma hat, is L inverse for LR being a scaling of phi x to doubly stochastic. So the solution of the operator scaling problem is basically Tyler's M-Estimator. You might wonder why we don't care about R. Well, this is because, just as in the matrix case, once you know L, you also know R. And there's an algorithm for quantum operators, which I just mentioned, Sinkhorn's algorithm, and it turns out that the iterative method for Tyler's M-Estimator is exactly the same as Sinkhorn's algorithm for quantum operators applied to phi x, where you just keep track of the left scaling L the whole time. Now let's see how geodesic convexity and quantum expansion can help us prove our sample complexity bounds. Geodesic convexity comes up because sigma hat can be seen as the minimizer to a certain function from the positive definite matrices to R, which you can think of as a log likelihood, actually a negative log likelihood. And F is geodesically convex on the positive definite manifold. So what that means is that we think of the positive definite matrices as a manifold by putting a metric on them, and this metric is going to induce geodesics that look like this. This curve is the geodesic going through a positive definite matrix P. For example, when P is 2, this is essentially isometric to the hyperbolic plane. So now here's a proof sketch of our sample complexity bounds. So first off, we can assume that the true covariance matrix is the identity. This is analogous to putting a distribution in isotropic position before you try to prove that the sample covariance matrix converges. So now with that, we can begin our plan. Firstly, we're going to show that F is strongly geodesically convex near the identity in the PD manifold. That is to say that it is strongly convex along every geodesic, suitably close to identity. Next, we will show that the gradient is small at the identity. That's actually just going to be random matrix theory. finally, using these, just like in the Euclidean case, we can conclude that the optimizer is not far away. So this sketch has some problems. The main issue is that the geodesic distance is more like the Frobenius distance and not the spectral norm. There's a fix for this, which is to use a stronger property called quantum expansion and use a result of Kwok, Lau, Ramachandran in 2019, which showed a similar bound as in the sketch, but with the operator norm instead of the Frobenius norm and quantum expansion instead of strong convexity. So what is this quantum expansion? Phi is a 1 minus lambda quantum expander if, as a linear map, its singular values obey this spectral gap equation. Remember, quantum operators can be viewed as linear maps, as we showed on a previous slide, and all it means to be a quantum expander is that there's a spectral gap for this linear map. Quantum expansion is to quantum operators as spectral expansion is to Markov chains and bipartite graphs. And 1 minus lambda quantum expansion is stronger than lambda strong G convexity. So in order to be able to apply this KLR19 result, we needed to show that phi x is a quantum expander in our setting. This is what we did. We showed that if the number of samples is at least a constant times p log p, this operator phi x we constructed as a 0.99 quantum expander with exponential failure probability. This fact is a quantum analog of a random bipartite graph being an expander. And this improves a bound from KLR19, the paper we cited, where they showed that the number of samples being p to the 4/3 is enough to obtain this quantum expansion result. So now I'll give a quick proof sketch for the iterative procedure. Here we'll use the fact that the gradient of the function, our log likelihood, is the error in the equation for Tyler's M-Estimator. Then we'll use some folklore, which is basically the same as the folklore from the Euclidean case, which is that if a function is lambda strongly G-convex near some starting point L0 and satisfied as a descent lemma, which says that at each step of the sequence, the function value decreases by something proportional to the gradient squared, then the gradient itself decreases exponentially. And the required convexity for the function will follow from the quantum expansion of our operator phi x. For future work, we want to remedy the situation, which is that practitioners usually have way fewer samples than the dimension, but they assume sparsity so that the problem is still well posed. We wonder if the operator scaling perspective can help in this situation as well. And we wonder what other models can be solved using geodesically convex optimization. Operator scaling is just one of the many problems that was recently shown to be tractable using geodesically convex optimization, so we think a lot of other models are suddenly much more tractable. Thanks for listening, and if you're interested, please check out the paper on arXiv.